Okay, so today we're going to continue to look at multivariable case, which is, as you remember, we have two inputs. So we like to think of them as X and Y, and we have an output. We might call that Z. And so today we're going to consider the problem of graphically representing such a function. Okay, now, if you start counting, you say you've got two inputs and one output, that's 3 dimensions. So in reality, to make a true graph, you need to do something 3-dimensional. And so this then becomes the classic problem of how you represent something in 3 dimensions in 2 dimensions. Okay, so one way you can do it is by using some kind of perspective. So here, for example, is an example that I think used a mathematical program called Mathematica to graph this 3-dimensional graph. And you can kind of see here's some sort of bottom of the valley here, and then around it, it kind of goes up and down, sort of like a roller coaster ride around that. And so you can think of a 3-dimensional graph as some kind of terrain in which you're going over. Okay, we are not going to be doing anything with this. So I just showed it to you just as an example of what you can do, but that's really a technology thing. I know some graphing calculators now can do these kind of graphs, but not all can. And it's a whole subject in itself, just doing that. So we're not going to worry about that. So that's left with, there's 2 other ways you can do it. Represent the function in kind of like a 2-dimensional graph, both of which you can do on pen and paper. So one is by using cross sections, and that's what we talked about yesterday. So the idea is if you have a terrain like this and you start doing a bunch of horizontal cuts, that'll give you just a normal function which you can investigate. So you can do horizontal cuts one way and then cuts another way, and by examining those cuts, you can figure out what the function is doing. So that's a nice, legitimate way of doing it, and it also sort of feeds into the strategy of handling these functions, which is to look at each variable one at a time. So you keep one variable constant, and you look at what happens when the other variable varies, and so that goes back then to the normal case that we studied in the rest of the semester. The other way to do it is another kind of map you've seen before, which is a contour map. So you've seen a contour map whenever you've gone hiking and you've got a map and you've got contours which show you the height of the land. Or if you look at a weather map, so here we've got a map, and on it it's got isotherms. So iso meaning equal, therm being temperature. And so these lines here, this is the transition between 70s and 80s. So everything on that line is at 80 degrees. Another weather map you might have seen is one which gives the pressure. So it gives you isobars. So you can figure out where the high pressure is and the low pressure. And then you can figure out, when storms are coming and all kinds of stuff like that. Okay, so this is kind of like a legitimate way of doing it. And so what it really is it's kind of taking this thing here in 3 dimensions, and then it's kind of like projecting it onto the floor here. You can kind of see the contours here. So you kind of take in, all you've got to do is like, you put in, well, where does z equals 0? Do that kind of cut, and everywhere it meets the graph, you just then draw that down here. Now you can do the same thing with z equals 1, 2, 3, and you end up with a bunch of contours. And really, it just, so if you look at this, you can really think that there's some kind of landscape over that, and that's the function. Okay, so you've seen these kind of things. So this is a weather map showing predicted high temperatures. So everything on this line, we predict to have a high temperature of 80. Here it's 90. Here is 100, 70. 70 here, 70 there. Okay, yeah. So you can kind of figure out what things are doing. Okay, and so we can say, okay, what was the predicted high today in Boise? And you look at here, and you see, well, the temperature is going to be somewhere in the 70s. Okay. Here is along here, it's exactly 70. Along here, it's exactly 70. So it's pretty close to 70. You know, it might just be a degree above, so you might guess like 71. Whereas if you go to Topeka, right, here's Topeka, we see that the high is somewhere in the 80s, right? But here we see 90s, here we see 70s, here we see 80s. Topeka looks like halfway between the 70s and the 90s, so we would say 85. So we can have a look at this and we can make estimates of what the actual values are. And what about Buffalo? Anyone like to guess like a high for Buffalo? 71. No, right. Here is 60s, here is 70s, here is 80s. I think you're going to go higher, right? This is almost at the 80s. So I would say something like 78, maybe, more like. So you can kind of think that here we've got isotherms in here, and you can kind of imagine like putting in your own isotherms of like intermediate values. Try and guess what that is. Okay, so the idea is this is a nice graphical way to represent information, to represent a function. Here's the type of contour map that you're probably more used to. Is like, does anyone go hiking? You use maps? Okay, you've got to be really hardcore to be able to look at a map and to be able to read. So some people can have a look at a contour map and they can say, oh, you know, this is what the landscape looks like. You know, because usually when I'm doing hiking, I just follow the trail. But you know, some people, if they're really rugged and going out into the wilderness, they need a map like this so they'll be able to figure out, you know, where's the water, so that kind of important stuff. And so there are people here who can look at this and they can distinguish features, right? So here, so if we can start to look, you know, we can start seeing, you know, 1300, 1500. So here we're seeing kind of like a rise. Here's 1700. So this looks like it's kind of like the top of it. There's going to be a hill here. Okay. And how do you tell the difference between a hill and a valley? One way the contours are increasing, the other way the contours are decreasing. So you can, with skill, you can actually look at this and have a very good idea of what the terrain looks like. Similarly, if we graphing a function this way with contours, so with a function, the contours could represent anything. So here we're measuring altitude. The map before showed temperature. You could have one showing pressure, but you could have one just in abstract space, you know, just showing whatever it is that you're studying. So let's, instead of having a look at a complicated map like that, let's have a look at something a little bit more straightforward. Okay, so here is a room, and we've got a window that we've opened. Okay, and this is temperature contours in the room. What's happening? Well, it kind of depends, right? It depends upon, so the room would have been at a temperature, the outside is at a temperature. And when we open the window, what's going to happen? The temperature from the outside is going to influence what's going to happen on the inside. Right? So these could be increasing contours or they could be decreasing contours. Okay? So for example, if we're in Minnesota in wintertime and we open the window, what kind of contours are we going to have? So the room, I've been in Minnesota in the wintertime, they keep it like toasty warm. Okay? So this contour might be like 80. Open the window, it's let me in the cold, so it might be 80, 70, 60, might be an example of contours, like if we just recently opened the window. So we're getting cold, the cold coming inside, and so we kind of see kind of like a valley of temperature. Get into the window, it's being like the bottom of the pit. But if it was in San Francisco, where the winters are mild, we'd still have like a pit. But what can you tell me about the contours? Yeah, it'd be fairly shallow. So it's the difference between steep and shallow. So in San Francisco, it might be, you know, this might be 75, 70, 65, or something like that. Again, so remember, there's always kind of two things you want to know about when you're trying to explain a function. Sort of like, one is it increasing or decreasing? So that, you know, that tells you something about a derivative, right, being plus or minus. The other is steepness. Okay, so if you've got big values for the derivative, then you're going to have something steep, and then you might have shallow. We haven't defined what a derivative is in this situation. We will in a little bit, or we'll next week. But you already can see, well, whatever it is, right? In this situation, it's going to be negative and steep. In this situation, it's going to be negative and shallow. What about Houston? Texas, man, it gets hot. There they keep, you know, in summertime, they've got the air conditioning on full blast. And it's stinking hot outside, right? So in that case, if you open the window, now instead of a valley, you're going to get a mountain, right? So the temperature is going to go here. So over here, it might be nice, you know, 65 or whatever ridiculous temperature they're keeping at. It might be 65, 80, 95, something like that. So we're going to expect increasing and steep. In Oregon, oh, nice there, if you go by somewhere like Portland or Astoria, sort of by the sea there, it's very mild. Again, you're going to have the same thing. It's going to have a little mountain, but this time it's going to be very shallow, right? So that might be 70, 75, 80, for example, could be a reasonable thing. Okay, so you've got to start getting in your mind, thinking about these contours and trying to go from these chicken marks or whatever they are, I think, into actually thinking in your brain what is going to happen. Oh, I don't want to do that yet. Make this work. Oh, here we go. Here, nice. So, for example, I can't get it to work, can I? Can you see that now? Right, okay. Not very well, can you? Better? Yeah. Okay, so if you look at this thing here, here is an example of a topological map, topographical map, sorry. And so here we're seeing contours, we're seeing circular contours. So here we're seeing circular contours going up. So we've got 1, 3. Okay. So what we've got is a little hill. Here we've got -1, -3. So we've got ourselves a little depression here. Here we've got 1, 6, 11. The lines are really close together. Okay, so if anyone who's done hiking and looking at the map, you know that if you see the map that the contour lines are really close together, that means it's steep. And that's what we see here. And so here it says 3,000, 4,000, 5,000. So we're expecting, you can think of a peak. Very good. Yeah. Here we've got, what's happening here? Here we've got 500, 300, 500, 300, right? So we've got something that's like that in that direction. But here now we've got 500, 800. So in one direction it's going like this, in the other direction it's going like this. So that's kind of like a mountain pass. Some people call it a saddle point. So this is like if you're building a road, that's the direction that you do it. So you go between the hills to either side. Here, instead of closed curve, we've got straight lines. So we've got 100, 100, 200, 200. So you can think we've got something like a U shape, but it's sort of going in that direction. So it's kind of like a long valley which sort of goes in that direction. And the most important thing about contours is here we've got a contour line of 100, here we've got a contour line of 200. This can't possibly be, right? Because remember, a function has a unique value at each point. So that means when you did like normal functions, you had the, remember the vertical line test? This is the same kind of thing. So at a given point, an x and a y, you can't have the same value. So this is impossible. So you've always got to have your lines separate. Yeah. Oops. Okay, so here is an example of a topographic map. And we're just using it because it's an example of a graph of a function in two variables, right? Because if you think about it, your place on Earth, it's kind of given by latitude and longitude. So that's like 2 bits of information gives you where you are on the Earth. And then the function is, given what place you are on Earth, how high are you above sea level? That gives a perfectly good function. And so if we can look at this and we can interpret that. So how many hills do people see? Does everyone see 3? So here, so you just look to see where the contours are growing, and you're kind of looking to, a hill should be sort of like a closed shape. So definitely we see one here. Definitely we see one here. And it looks like there's one here. It's sort of cut off, but we can see that's there. And so we can estimate then the coordinates of where the hills are. So here we go 7. So we do the horizontal coordinate first. 7, 2. Here it's 3, 7. Here we're going to estimate that the top of the hill is here. We're not 100% sure because we don't know what happens over here, but it kind of fits this because we can see these sort of U-shaped type things. So it looks like the top of the hill is around here, which is around 0, 2.5. Which hill is the highest? Yeah, here. And that's easy. You just look for the highest contour number. A river runs through the valley. In which direction is it flowing? Oh man, this is, you didn't realize you were doing geography today, did you? Okay, how would we be able to note where the river is? How can we tell what geographically tells you that there's a river somewhere? What's the landscape like around a river? Around the river. Yeah, you expect like some kind of valley, right? And water flows from high to low, right? So if we know that there is a river valley, then we know it's going to go from the high point to the low point. So here we see a high point, here we see a high point, here we see a high point. Here we see the low points, right? So to my eye, it looks like it's kind of running northeast. So it'd be going between these hills and going off in that corner. Okay, so now let's go from a real landscape to an abstract landscape. So this is a map that shows corn production. Okay, and so instead of having latitude and longitude, we have variables that determine how much corn can be made. Okay? So how much crop yield you get is going to depend upon how much rain there is and what the temperature, so this would be like average summer temperature or something. Okay. And so now the contours here are of corn production. So basically it's saying that anytime you've got this combination of temperature and rainfall, this is how much corn you're going to produce. And 40, 50, 60, 60. Okay. And here's the peak, 113. So this then is the ideal weather for corn production, and it is, what is it? It's like 19 inches of rainfall, and it's, I don't know, like 74.5 degrees or something. And then you get the most corn. Okay. And so we can say things like, well, what's F of 1878? You can read it off the corn, off the thing. So here's 15. Here is sorry. So 15. This thing here is 1576. That's where we're at the present. So with the present temperature weather conditions, we can produce 100 units of corn. Oh, I think this represents percentage. So here we are at the moment. So that's our current yield. We're at 100%. So this is what happens when the temperature changes. So if it was 1878, we'd be able to produce the same amount of corn as we do under these conditions. If it's 1276, 1276 is going to be here. Okay, we're going to be producing less corn. It's going to be less favorable conditions for doing corn. And what's that going to be? Maybe it looks like at 86, 87. So under these weather conditions, we can only produce 86% as much corn as we can under the present conditions. But when you look at this, you should be thinking of a hill, right? So it's an abstract hill. Maybe it's a hill made of corn, I don't know, but it's an abstract hill, right? And here is the optimum place to be. It's at the top of the mountain. And so obviously this is going to have something to do with calculus. Because if we want to reach to the top of the mountain, we've got to have some way of figuring that out. Because we've done these optimization problems before. So you know that's something to do with setting a derivative equal to 0. Right. So at the top of the mountain, it's going to be flat, right? Because there's no more way to go up. And so that's what we'll be doing next week, is learning the techniques to be able to do that. Here's another sort of abstract. So Cobb and Douglas are famous economists from early 20th century, and they were looking at businesses and trying to figure out sort of what are the, you can think of, you have a business, right? And you have various ways that you can spend your resources. So you can think of those as kind of inputs into your business. And so typically what you think of it is you've got money. Okay? Am I going to spend my money on this or that? And they did this simple thing where they just thought of two variables. So you could spend money on capital, money on, like getting equipment for, so for example, this is what is this? For printing production. So you can spend money on like machines and stuff, or you can spend money on labor. Okay. So what is the best mix of labor to capital goods? So the idea is you want to be able to maximize your production. So they had this idea of, they eventually came up with these things called the Cobb-Douglas production function. And so the idea is that it's kind of multiplicative function. So the idea is if you have twice as much labor, then you're going to have more production. It might not be twice as much. It's going to be some sort of allometric relation. It's going to be some sort of power. So it's going to, you're going to have n to some exponent alpha. But alpha is going to be between 0 and 1. The same is going to be for your other thing, so your equipment. Again, if you have twice as much equipment, you're going to be able to produce that increased production by some 2 to the beta. So where there's some sort of allometric thing going on here. And the idea is that capital and labor are kind of independent of each other. So you can just model whatever gains you get, you can just sort of multiply them together by. So this was the model that they came up with. And so these kind of functions, they're known as Cobb-Douglas production functions, and they're a standard thing that people study in economics. So, given that this is what the production function looks like, it's a function of two variables, right? N and V are going to be your variables. C, alpha, and beta are just parameters that just depend upon whatever business you're in. And P is the output, right? So you've got two inputs and you've got one output. So here we've got some contours for it. And one's correct and one's incorrect, and I've already told you the answer here. This is the correct thing. So, like for example, why is this the same, the correct thing? So if we've got P equals N Z, for instance, let's just take all the parameters equal to 1, just to make it easy to analyze. Then if we fix production, say we fix production, and so now we want to graph N and V, so we see that V equals 1 divided by N. So we expect to see things that look like hyperbolas. And this is how we got this kind of thing here. And so then the next production level would be 2. And then you get 3, etc. And so you end up with these contours of hyperbolas like this. And so here is your production. And hopefully this kind of makes sense. So you see that, say, for example, you're here. How much money does it take to do that? Well, it takes this much money and this much money to produce that. you can kind of see that it's kind of like the optimum thing. You've got to sort of balance your capital versus your labor to be able to get the optimum thing. So it's not always is this thing's going to be 1. If everything is 1, then the best thing to do is just to be equal between n and b. But if these are different numbers, then you get different proportions that's going to be. Okay. Now, the thing that you're all scared about is that I'm going to ask you to make a contour map, and I will. So this is the basic idea of how you go about making a contour map. So remember, we had this example yesterday of a revenue function. And we want to make a contour map for that. So the first thing you've got to do is you've got to decide what your contours are going to be. So in this question here, I've told you what the contours are. So the contours are going to be 4,000, 8,000, 12,000, 16,000. Well, if you go ahead and write these down, these things are just straight lines. Okay? And so if we take one of them, so let's take this guy here. What are we going to do? We could just solve for y. We get 4,000 minus 350x divided by 200 equals y, which means y equals, so we get the thing in front of the x is going to be the slope. So what's that? That's minus 35 on 20, minus 7 on 4. And then we've got the y-intercept is 4,000 divided by 200, which is plus 20. And you see that what happens as you go from 4,800, 12,000, 6,000, you're just changing this number. And so you're just changing the y-intercept. So the next one is going to be y equals minus 7 on 4x 40. And it's y equals minus 7 on 4x 60. And then finally y equals minus 7 on 4x plus 80. So that gives you a bunch of equations. And so now we just sketch them. Okay, so now we have our y, and we have our x. So minus 7/4, right, is just a downward sloping line. And it's got different intercepts. So we can say 20, 40, 60, 80. Minus 7/4 sort of goes down like this. Oops. These should be parallel. And of course, nothing should be negative. Right, so x and y are inputs. And so we see it just kind of looks like that. And so here is the 4,000, 8,000, 12,000, So the last thing is you put in what the values are. And so what is it? We see that the landscape is just like a linearly increasing hill in front of us. It just sort of goes up like that. And that's exactly what kind of thing. So the idea, right, is that again, we're fixing something. So the idea is when you've got a function with two inputs, you've got three variables. So always what you do is you fix one and look at the relationship between the other two. And that will get you through any question. Okay, so here we have contour lines crossing, but this is allowable, right? Because it's the same, it's got the same value, so you don't have. So what is happening here? So here is so 0 seems to be the lowest point. And so when I'm here and I look around, what do I see? Yeah, there's a hill here, there's a hill here, there's a hill here, there's a hill here. It's flat along these things here. So it's probably a mountain pass. So we're in between mountains there. It's definitely not a mountain top. To be a mountain top, we have to have the contours go the other way. It wouldn't be B or D because that would be kind of more like a ridge would be kind of like you have just in it'd look like this, but just in one direction. So it'd sort of go in a direction and it'd be kind of like that. And so you'd only have the zeros in one direction, and then you have lines going up it, going down. And if it was a dry riverbed, they'd be going up. Are the values of contour lines always 1 unit apart? No, because steepness varies, right? So if we have contour lines that look like this, that shows something which is kind of flattening out. Any contour diagram that consists of parallel lines comes from a plane. That's not true. That's another counterexample over here. Because like if it was in a plane, it would be constant decline. This is true. A contour diagram of any plane consists of parallel lines. The parallel lines are going to be equidistant. So this is that's kind of more like what a plane looks like. Contour lines can never cross, that's true. The closer the contours, the steeper the graph of the function. That is also true. Okay, so let's just kind of finish off with this one. Let's do this surface here. Very easy one. Z equals 1 minus x minus y. So let's do some contour lines. So let's do contour lines for -2, -1, 0, 1, and 2. So we get -2 equals 1 minus x minus y. So that means y is over here is 3 minus x. Minus x. So that contour looks like that. If we do -1, that changes it to 2. So this is -2. This guy here is -1. If it's 0, here. I'm getting the hang of this. This is 1. This is 2. Okay, so this is a plane. Okay, if we start on here, let's put an ant on here. In what direction should they go so that the altitude remains constant? They just have to stick to this line, right? So they have to go either, what's this, northwest or southeast, remain constant. In which direction does the altitude increase most quickly? Yeah, going in this direction. And that's also a kind of always true as well. So if the contour lines are where things are constant, perpendicular to the contour line is where the steepest route is. Okay, we've got time for this. Here is a function. You stand on the graph of the function. -1, -1, 2. So that must be here. And start walking parallel to the x-axis. Okay, so we start walking in this direction. What do we see? Yeah, we're sort of going down, and then we go up. And how steep is our path? Well, we don't really know what it represents. But the thing is, it's starting off, it shallows out, it sort of bottoms out, it's fairly shallow here. And then what happens when we start getting here? It starts getting steeper, right? Okay, that's today's class.